Today we're going to focus on applying the properties of exponents and evaluating the zero exponent. So yesterday we really worked on learning what power is and evaluating a power. We're going to keep working with those powers, but more with bases that are variables instead of numbers, although they can be numbers too, okay? Take a second to pause the video, complete the warm-up, and copy down your target. Okay, so now that you've completed the warm-up, when you're comparing 10 to the third and 3 to the 10th, what did you notice? Typically, it's better for the larger number to be in the exponent than it is for it to be in the base, although there are exceptions. Here I have 3 squared, which would give me 9, and 2 cubed, which would give me 8. So normally, you'll get a larger number, a larger result if your larger number is in the exponent, but this is an exception to that, okay? So give at least one exception. This may be one that you have. Maybe you have another one as well. Also, I wanted you to make a table of values that shows some support. I said, okay, 5 cubed is 125, and 3 to the 5th is 243. Just one example there. Hopefully you have a couple more, but here I can see the larger number in the exponent gives me a larger result. So with multiplying powers, let's think about this. The factors of a power, such as 7 to the 4th, can be grouped in different ways. Notice the relationships of the exponents of each product. In this first line, how would you write this in exponential form? 7 times 7 times 7 times 7, 7 to the 4th, right? Well, I still have the same number of 7s, so in the end, I'm still going to get 7 to the 4th down here. But how do I write them to represent the parentheses here? If I did these 3 first, how would I write that with an exponent? That would be 7 cubed, right? And then I'm multiplying 7 cubed times 7, and I'm getting 7 to the 4th. We'll look at the next one. How would I write this in exponential form, making sure that I'm representing these parentheses that you see? Well, this would be 7 squared, and I'm multiplying that by this, which is also 7 squared. So do you notice a pattern here? Could you make up a rule where if I'm multiplying the same base, you would just do something to their exponents? Here I'm multiplying the same base. I have an exponent of 3 and an exponent of, well, we don't see it, it's 1. Somehow I got 4. On the next one I have an exponent of 2 and another exponent of 2. I'm multiplying the same base and I got 4. What are you doing with those exponents? Well, hopefully you see it. What you're doing is adding them. To multiply powers with the same base, you're going to just keep the base and add the exponents. This will always work. Okay, so multiplying the same base, you can add the exponents. Now, it only works for the same base, so make sure you write that in. So, for example, 3 to the 5th times 3 to the 8th would be 3 to the 5 plus 8. And I do want you to write that step. So it comes out to be 3 to the what? 13. Well, here's an algebraic way of writing it. If you have b to the m times b to the n, same base, you're multiplying the same base, so you would add their exponents. B to the m plus n. So let's try these on A, B, C, and D under example 1. I do want you to make sure you show me the addition step. It'll take you 1 extra second, so I don't want to hear any complaints, but that's going to be the only work that you have. Complete these 4, then pause play to check your work. Hopefully here you have 6 to the 6 plus 3, which is going to give you 6 to the 9. On B, n to the 5 plus 7, or n to the 12th then. On C, tricky here, what did I say the exponent was if you don't see it? It's a 1, so don't forget to do x to the 5 plus 1 plus 32. If you have 37, you're 1 short, you should have x to the 38th. And on the bottom left here, we have a 4, a 1, a 17, and a 3. So we're going to have 24 for the 4 plus 1 plus 17 plus 3, or 24 to the 25th power. We're not evaluating these, don't worry. I wouldn't ask you to do that without a calculator. And notice the directions. It just says write the product as 1 power. So it doesn't even want us to evaluate it. We just had to write the product with 1 power. Now we're good. Okay, so remember that when you're multiplying the same base, you add the exponent. Multiplying the same base, add the exponent. Say that a couple times to yourself. Well, then what do you think is going to happen for division? If when you multiply the same base, you add the exponents, when you divide the same base, what do you think you do? Let's expand this out and see what makes sense. We know how to represent 5 to the 5th power expanded out. It'd be 5 times 5 times 5 times 5 times 5. Expand out 5 cubed. So you have a product within a fraction. Well, remember in math, if you have a product in a fraction, only multiplication, you can reduce them. The 5 in the numerator would cancel this 5 in the denominator. Same with these two. They would cancel each other because I'd be multiplying by 5 and then dividing by 5. Multiplying by 5 and dividing by 5, those would cancel as well. Cancel out everything that you have in both the numerator and the denominator. I can't cancel anymore because I'm out of them in the denominator. So I'm left with just 5 times 5, which is 5 squared. Is what you thought correct? When you're dividing the same base, what do you do with their exponents? Hopefully you're saying subtract. To divide powers with the same base, keep the base and subtract the exponents now. Makes sense. When we multiply the same base, we add it. Again, these rules only work for the same base. So if I'm doing 7 cubed times 5 to the 4th, I can't do anything with that unless I find what these numbers actually are. But if I'm doing 7 cubed times 7 to the 4th, I can add those exponents because I'm multiplying and get 7 to the 7th. Or if I'm doing 6 to the 9th over 6 to the 4th, I can do 6 to the 9 minus 4 this time, and I get 6 to the 5th. Or in the algebra terms, b to the m minus n. Okay, so 2 quick examples here on dividing. Write the product as 1 power. You probably already have your answers down, but I want to see the work. So it's 7 to the 5 minus 3. When you're dividing the same base, you subtract the exponents, 7 squared. Don't evaluate this because it doesn't say to. It says leave it as a power. And on the next one, x to the 10 minus 9, which is x to the 1, which you don't need that 1. You can just write x. Okay? Your teacher probably won't take off if you write the 1, but you should know that it doesn't need to be there. You don't need to see it for it to be there. So think about it. When the numerator and the denominator have the same base, and exponent, if you subtract the exponents, you're going to get 0. We need to know then how to evaluate 0 in the exponent. What is 0 in the exponent? Well, let's talk about this. 0 power of any number except 0 equals what? So like I said, if I have 5 squared over 5 squared, if I do the exponent rule, it would give me 5 to the 2 minus 2, which would give me 5 to the 0. So what's that equal? Well, guys, remember in math, what's anything divided by itself? 1. So 0 exponent is going to give you 1. 100 to the 0 exponent is 1. Negative 7 to the 0 exponent is still 1. 5,280,000 to the 0 exponent, still 1. The only thing that doesn't work for this is 0 to the 0 power. Okay? Why? Well, let's think. If we have 0 to the 5th power over 0 to the 5th power, the only way I could get a 0 exponent would be a problem like this. I'd have 0 to the 5 minus 5, which would give me 0 to the 0. Go back to what you started with. What's wrong with this step right here? What are you not allowed to do? You can't divide by a 0. We're not allowed to have 0 in the denominator. So that is why 0 to the 0 power is undefined. That's what I want you to write down. It's undefined. It doesn't have a value. We don't have something we can assign to it. It's undefined. You cannot do it. All right, last example up here. Light year, or the distance light travels in 1 year, is almost 10 to the 18th centimeters. To convert this number to kilometers, you must divide by 10 to the 5th. How many kilometers is it then? So we're taking the light years traveled in 1 year, and we're dividing it to convert it. What do you get? 10 to the 13th. All right, guys. You have an extra challenge right after this.